conversions. All right, so on page 135, we are titling this The Mole and Mole-to-Mole Conversions. That is what we are starting with today. Kevin, not a toy. The Mole and Mole-to-Mole Conversions. Notes in our notebook. About 10 more seconds to write the title. So we're going to be going over this for the next, literally 4 weeks in class, because it probably takes 2 weeks just to understand the content for some people. Some people will get it faster than that. It's just dimensional analysis. Each time we do a lecture, you're also going to get something new this quarter called a doodle note. So I'm going to pass this page out to you tomorrow so we can review it, or if we have time today. And we'll get to learn this. This will go as a process page into your notebook, but it's a doodle note, so you can draw on it, color it in however you want to help retain this information. But we're going to be going over that a little bit more. Today, my goal is to get through the slides and get through the practice problems on your process page so that I can send you home with some practice problems to do. The instructions for your color group are on campus. And then we'll go over these tomorrow. Questions on the agenda for this lecture? Okay, so Rafa, at this point we are not cutting and gluing in a notebook. Okay, cool. So, what's a mole? Okay, a mole is an animal. That's probably the thing that you know, but that is not what a mole is in chemistry, okay? So the mole is just a unit of measurement, kind of like a dozen. Actually, exactly like a dozen. So the mole, this is Millie the mole. The mole just represents a specific number of things. Okay, so how many is a dozen? 12. A mole is the exact same, except instead of 12, it's 6.02 times 10 to the 23. So it's a huge number. It's actually 6 sextillions. That's what this means. And it's also called Avogadro's number. So he's a scientist, not avocado, although if you say that, I'm not going to mark you off on it. It's a lot easier for people to remember. I've had people on their test, instead of writing 6.02 times 10 to the 3, just draw an avocado. I know what you mean. That's cool with me, as long as you can solve the problem. So holy moly, or holy guacamole if you're going on the avocado route. A mole is just a unit of measurement. It is a specific number of things. It's called Avogadro's number. So 1 mole is equal to 6.02 times 10 to the 23. 1 mole is always equal to 6.02 times 10 to the 23. So how many dogs is 1 mole of dogs? 6.02 times 10 to the 23. How many students is 1 mole of students? 6.02 times 10 to the 23. All right, how many pencils is a mole of pencils? 6.02 times 10 to the 23. What about 2 moles of pencils? What would I have to do to this number?
12.04 times 10 to...
The scientific notation was a little off, but I haven't taught you that yet, so yes, perfect. So, because scientific notation has to be between 1 and 10, so you would actually do 1.2 times 10 to the 24, but all you do is multiply this by 2, which is exactly what you did. 12.04 times 10 to the 23. So if I needed 2 moles of something, I would just take Avogadro's number and multiply it by 2. Beautiful. So take about, how much time do we think we need? Maybe 30 seconds?
Yeah.
30 seconds? Take 30 seconds to make sure you're caught up on this slide. So not 30 seconds to talk, please, because some people can't write and talk at the same time. More seconds. All right. So people think that a mole is really, really complicated because it's this huge, big number. It's not. It's just like a dozen. Okay, so if you have a dozen donuts, how many donuts do you have?
12.
Same thing with a mole. If you have a mole of donuts, how many donuts is it? 6.02 times 10 to the 23. Now, why do we use it? Everything in chemistry is super, super small, and scientists are also lazy. Okay, if I had to write out 6.02 times 10 to the 23 atoms every single time, I'd probably get a hand cramp. Instead, I can just write 1 mole. It's like half as many things to write down. It's way awesome. Okay, and also everything in chemistry is tiny. So have you ever like held a sewing needle before?
Yes.
Okay, so on a sewing needle, let's say you dip that sewing needle in water. Okay, on the very tip of that sewing needle, there's 9 billion atoms of water on that. Okay, on that tiny little tip. So an atom is so, so, so tiny. So we use the mole because we have to use a lot of it, right? So if I actually want like a cup of water, that's going to be so many moles of water. So it's way easier to write a mole than it is to write 9.0 times 10 to the 75 atoms of water, or what might be there. Okay? So because of these two things, we abbreviate our numbers down to moles. It's much easier to think of something as 2 moles than it is to think of something as 4.5 times 10 to the 92 atoms. Okay, so moles are the most common unit that you'll see, but you will also see measurements in grams, particles, or something called formula units. Take maybe a minute and a half on this slide, and then we'll go into how we use them. One minute. Seconds. 30 seconds left on this slide. Okay, so stoichiometry is something that exists because we're not always given things as moles, okay? When you do an experiment, do I tell you to grab 2 moles of a substance?
No.
What do I tell you to measure out?
Grams.
Yeah, usually grams or milliliters, right? Because that's what we actually physically use to measure. We don't have anything small enough to measure 1 mole at a time. So we measure it in grams and we measure it in milliliters. But we often have to convert from one unit to the other if we need to know how many moles there are, if we need to know how much of something we can make, if we need to know if we did the experiment right. So you have to do that. That's all stoichiometry is the conversion from one unit of a substance to another. Right, so in the beginning of our apothecary performance test, we did like how many miles are in 10 feet, or how many seconds are in 365 days. Do we remember this?
Yeah.
Great. So that is stoichiometry already. It's just unit conversion, right? So stoichiometry is just taking one unit and making it another unit. Except this time, our unit will be something like grams of hydrogen peroxide, and we're trying to convert it to grams of oxygen. And that'll let us know if we're doing the experiment correctly, how much of it we can make, and if how much goes into it so that we don't cause any lab accidents.
So is it like balancing equations?
Balancing equations is part of it, but no. So balancing, that was actually a great question. Okay, so balancing equations tells us that we have x on the first side and y on the second side, and they have to be equal. But now, instead of just the numbers, because the numbers in balancing equations are moles, right? So let's say that I have H2 plus O2 goes to H2O. Okay, do I need coefficients for this one, or is it balanced?
You need coefficients.
I need coefficients, so what do I have to do?
You need to make the O's the same.
How?
I think if you multiple...
Put a 2 in front of the H and then put 2 in front of the H2O.
Yeah, that's big 2 involved.
Why?
So that there will be 4 H's and 2 O's.
Mhm.
Right?
Okay, beautiful.
Yeah.
So now this is a mole. That means we have 2 moles of hydrogen plus 1 mole of oxygen makes 2 moles of H2O. But I can't measure that out. So then I would have to use stoichiometry to figure out how many grams that is. Right, because I can't measure out 2 moles of hydrogen. It's impossible. It's so small. But I can turn that to grams to figure out how much I have to measure. Okay. So, you jumped the gun. So I'm going to actually leave that example up. When we have a chemical equation, we have coefficients before each item to tell us how to balance the equation, which was just what Von May's question was. Okay, so by making these coefficients a ratio, I can convert from moles of one substance to moles of the other. And then go ahead and write this example down with it, because that's going to give us some coefficients to look at for our mole ratios. And all you need to do to be good at what we're doing today is know how to find a mole ratio. That's it. So for today, if you can find a mole ratio, then you'll be able to convert between one to the other. Take maybe 30 seconds on this slide. Okay. So we are going to do the examples for this. That's it for notes today. All right, so switch to your process page, because mole ratios are way easy to see, but not as easy to just take notes on. So go ahead and flip to your process page for me, please. All right. You don't need that yet. Well, you'll see it every time. Okay, so you have a process page that looks like this that may or may not be glued into your notebook, but should be glued into your notebook before you leave today. We're going to try and get through as many of these as we can, and then I am going to give you your doodle notes page if we have extra time. If we don't have extra time, we'll do it tomorrow. So, starting with this one. So we have the equation N2 plus 3H2 goes to 2NH3. All right, is everyone with me on this?
Yes.
Okay, so what I'm going to do is I'm going to highlight my coefficients here. What's my coefficient for N2?
1.
Yeah, it's 1. What's my coefficient for H2? 3. What's my coefficient for NH3?
2.
2. Great. Okay, so those are my coefficients. But now I'm going to look at my problem and actually see what it's asking. This says how many moles of hydrogen are needed to react with 2 moles of nitrogen. So what is my given? What am I given? 2 moles of nitrogen. And how do you know that that's my given?
Because there's 2 in
Because it says it.
Yeah, because it gives me a number. If you have a given, it's because it actually told you what you're looking for. Okay? So it told you what you're starting with. Sorry. So my given is 2 moles of nitrogen because you always start with the one that has the number attached. So what should I be putting in my first box here?
2 moles of nitrogen.
Yeah, so I'm going to be putting 2, and I'm going to write it in orange because that's my given. 2 moles of nitrogen. Okay, now I hear a lot of talking. Is there a question? Okay, so let's pay attention, please. All right, how many moles of hydrogen are needed to react with 2 moles of nitrogen? So, how many moles of hydrogen? So what am I trying to get? What should my answer be in? I'm starting in 2 moles of nitrogen. What am I trying to get to?
Hydrogen.
Yeah, moles of hydrogen. That's what I'm trying to get to. Okay, now, here's where my mole ratio comes into play. How do I cancel out moles of N2? Where is this written right now, the top or the bottom? So where do I need to write the next one? The bottom, because I need to cancel it out. So I'm going to write my moles of N2. Now, where do I get this number from? I'm trying to use a mole ratio. So what gives me the mole ratio? The what? The coefficients. What's the coefficient of N2? 1. Okay, so now I have moles of N2 at the top and the bottom. What does that mean I can do with that unit? I can cancel it out. Moles of N2 is done. Moles of N2 is done. Now what am I trying to get to?
How many hydrogen?
Moles of H2. Now what's the coefficient for H2? 3. So now I have 2 moles of nitrogen, 3 moles of H2, and 1 mole of nitrogen. So now I crossed out these units and I'm just left with the numbers. So I have 2 times 3 divided by 1. What's 2 times 3 divided by 1? 6 what?
6 moles of hydrogen.
Moles of hydrogen. Yep, for now that's it. You just did your first stoichiometry problem.
First what?
So,
Trigonometry.
I have a question, and it might also be your question, so I'd love for everyone to hear it.
so in the product of the chemical equation, there's 6 hydrogen there. So would that also be the same?
Not necessarily, because it's not how many hydrogen did you make. It's if you started with this number, how many did you use? Yeah, that's good. All right, any other questions on this one before we do a second example? No need to shout.
Miss, is there like do you have to do this in order to know how many moles there are, or can you just look at it and see how many moles there are?
That was Peyton's question, so you have to do it because these numbers change. Right? So it's not just like how many moles do I have, it's how many did I use if I started with this. So because I could change this number to like 9 and get a different amount.
Oh, because the coefficient you have to make it 9.
So your coefficients don't change because that's the equation, but this number does. So let's say that I actually made that 9. Now what's 9 times 3 divided by 1?
27.
27.
So you have to do it.
So that's why you have to do the problem. Does that make sense?
Yes.
Because this number this stack won't change, but this number will, and that will affect it.
So like in the problem above like that, does it change with the 9?
Does which problem change?
Like you know how you have the 9 moles of nitrogen now?
Uh-huh.
So do you change it at the equation?
No. Because this is a given, it's not a coefficient. Do you see how the coefficients are in green here? But this one's not?
It's it's like a word.
Because this, perfect. Because it's like a word problem. Is that a stretch or a question? It's cool if it's a stretch. Okay. No, don't apologize for stretching. That is your God-given right. You can stretch when you need to. All right. So this one I have 2KClO3 goes to 2KCl plus 3O2. That's my equation. Let's underline our coefficients. What's the coefficient for KClO3?
2.
What about for KCl?
2.
What about for O2?
3.
Beautiful. Now let's read the question. How many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate, KClO3? What's my given?
6.
6 moles of KClO3. What am I looking for?
The moles of oxygen are produced.
Moles of oxygen. Beautiful. So what's going to go in box number 1?
6 moles of potassium chloride.
What's potassium chlorate?
KClO3.
Okay. Now I have that on the top. Where do I need to put it? The bottom. So I'm going to put moles of KClO3 on the bottom. Why?
So it can cancel out.
So it can cancel out. How many moles am I going to put?
2.
Why?
Because it says 2 in the front.
That's the coefficient.
Boom. Okay, now what am I trying to get to?
Oxygen.
So I'm going to put moles of oxygen on top. And what am I going to put? How many?
3.
I heard 2 and I heard 3. So which one? Why?
3. Because it's the coefficient.
3 because it's the coefficient. So what is 6 times? So remember, multiply on top, divide on the bottom. What is 6 times 3?
18.
Divided by 2? 9 what?
9 moles of oxygen.
9 moles of O2 because we crossed out
Okay,
this
so you
unit.
said multiply it on top
Uh-huh.
and then
This times this, the whole thing divided by the bottom. Questions before we go to number 3? Kyla.
okay, let's start.
All right, so I'm hearing some chit chat from the back. Is there a question in the back? Are you sure? Okay, I'm a good listener, I promise. All right, so we'll again get some more practice tomorrow. If you just got here, I will catch you up as fast as I can. You probably will not understand the process page, but that is okay. We will work on it literally for the next 4 weeks.
So, wait, we finished the 4 Q by ourselves, right?
I am going to give you the rest of these process page answers, and then you're going to have a practice page to take a look. Okay,
Is the practice page a grade?
so,
Is the practice page a grade?
sure, I'll sticker. I have to buy stickers, but yeah. Okay, I'm gonna sticker practice pages. All right, so, how many, or let's do our coefficients first. Zn plus 2HCl. Shh. There's a lot of talking. Zn plus 2HCl, ZnCl2 plus H2. What are my coefficients? What's this one? 1. What's this one?
2.
What's this one?
1.
Beautiful. All right, what's my given?
3.
3 moles of zinc.
3 moles of zinc. What am I looking for? Moles of hydrogen. How do we know that's what we're looking for?
Because it seals it.
Hydrogen are produced.
Beautiful. So it says how many. If it starts with how many or how much, this is your clue that that's going to be your answer. Okay? So what goes in my first box?
3 moles of zinc.
Why?
Because it's a given.
That's what we're trying to find. We're trying to find.
No, it's what we get.
We are trying to find hydrogen. This is our given, not necessarily what we get. Okay, it's on the top right here. How do I cancel something out on the top?
I put it on the bottom.
Putting it at the bottom. And how many moles of zinc am I going to put?
1.
Why?
Because we're trying to cancel
It's the coefficient.
It's the coefficient. Yes, I'm trying to cancel it out, but I get the 1 from my equation. I make my mole ratio. So a ratio is a fraction, right? So I'm going to put the coefficients on top of each other. Now, what am I trying to get to? Moles of what?
Hydrogen.
Which one of these is hydrogen?
The last one.
The last one, H2. And what's the coefficient?
1.
So I'm going to put what right here? 1. Okay, now I multiply on the top, divide by the bottom. What's my answer?
3.
Why?
Because 3 times 1 equals 1, and then divided by 1 is 1. I mean 3.
Beautiful. Now I only got half an answer, so what's the rest of it?
3 moles of hydrogen.
Hydrogen.
Beautiful. Okay. So how many moles of oxygen are necessary to react completely with 4 moles of propane? Let's do coefficients first. What's my coefficient? What's my coefficient?
3.
4.
So 1, 3, 3, 4. What's my given?
4 moles of
Whatever.
what is that, propane?
Propane. 4 moles of propane. Propane. What am I looking for?
How many moles of oxygen?
Yep, because it came after how many moles of oxygen. All right. So what do I put in the first box? What's my given? What's the number?
Moles of propane.
4 moles
H8.
of C3H8. What's my next step?
You put moles, not one, but like you put propane at the bottom.
And how do I figure out how many to put?
1, 3.
Well, that's the number. I put 1, but how do I figure out how many to put?
The coefficient.
Yeah. All right. What am I looking for?
The amount of oxygen.
Yeah.
So what do I put right here?
3 moles of
Oxygen.
Why 3?
Because that's the coefficient.
The coefficient. How do you know that something's a coefficient? Vale. Huh?
Because it has a number on the side of them.
Yeah. So what's 4 times 3 divided by 1? 12 what?
Oxygen.
All right. We got one more problem to solve. This one's a little bit tricky because I don't give you what each thing is. Now, this let's do our coefficients first. K3PO4, what is the coefficient?
1.
ALNO3, what's the coefficient?
3.
KNO3?
3.
ALPO4.
1.
Beautiful. Now this says, how many moles of potassium nitrate are produced when 2.5 moles of potassium phosphate react? What's my given?
2.5 moles.
Potassium phosphate. All right, how many moles of potassium nitrate? What's this?
2.5.
Nope, what is this?
K.
Moles of potassium nitrate is what?
K.
Why is this important? What is it? If this is our given, what is this?
The answer.
Yeah, it's what we're looking for. It's our answer. So I'm going to underline moles of potassium nitrate. Now we're going to figure out what each thing is. My given is 2.5 of potassium phosphate. Which one of these coefficients do we think is, or of these equations is potassium phosphate? What's potassium?
K.
What is potassium?
K.
K. What is phosphate going to start with?
P.
PO4. That's my whole thing. So I'm going to start with 2.5 moles of K3PO4. What's my next move?
Well, you put the same thing at the bottom to cancel it.
Yeah, but how many?
1.
Why 1?
Because in the equation there's only 1.
Because that's the coefficient from
The,
where?
the equation.
The equation. Coefficients come from the equation. Now, what do we think potassium nitrate is?
KNO3.
Why, Rafa?
Because potassium is K and nitrate is NO3.
Are you
Beautiful.
enough?
All right, and how many are we putting right there? 3. What's 2.5 times 3?
7.5.
7.5 divided by 1 is
7.5.
7.5. So what's my answer?
7.5 moles of KNO3.
Moles of KNO3. Okay,
Watching the hard
So-
overtime.
that was such an enthusiastic bid. Please grab an assignment from the purple bin. The more you get done, the better of your chance of a sticker. We'll go over the right answers tomorrow.